Hello, welcome to this improved digital module on deformation measurement techniques. My name is Halldór Geirsson and I'm an associate professor at the University of Iceland. As the title suggests, we're going to look at some different methods of measuring crustal deformation. So, crustal deformation processes, there are many aspects to that, and we can measure that in many different ways. So to summarize some of the processes that we may be looking at, we can think about, for example, plate motion, plate boundary processes, so how strain is accumulated at the plate boundaries, and how then the strain is released in earthquakes, and a whole bunch of phenomena that comes with that. We may be looking at volcanoes, how magma is moving, whether it's accumulating or if it is leaving magma chambers, forming dikes and sills, or some time-dependent conduit or magma chamber processes. We may be looking at the end products of eruption, so lava compaction or maybe even inflation of these lavas while they are growing. Some people look at landslides and use for that geodetic techniques, and there we have some different modes of movements. There can be slow creep that just is ongoing for years and decades. Then there can be catastrophic failure, which takes maybe only seconds or tens of seconds. We also have loading and unloading events. So many of us maybe know glaciers. They are melting now, and when they melt, the ground is uplifted. But we can also have similar deformation just from seasonal changes in the snow load, just if there's a lot of snow or not. And same applies to lakes and variations in elevation of lakes. And some other loading processes also exist. So, for example, if we have a lot of lavas that are erupted, or even just whole volcanoes and placed over long times, and these sort of large-scale erosional and sedimentary processes, they also are really long-term deformation events as well. We also have geothermal power production in some places, for example in Iceland and Italy, and there is some deformation, some centimeters per year, that's associated with the extraction and then also injection of fluids. Finally, there can also be some mining-related deformation, and that's usually on rather small scales and relates to fluids being extracted or injected to mining areas. So these are all different processes. They're acting at very different spatial and temporal scales. And likewise, there are a lot of different techniques that span different scales, both in time and space, to survey this. So many may be familiar with some of these techniques, like GNSS and INSAR, which are sort of the basic techniques that are applied currently to study crustal deformation. But I wanted in this presentation to go a bit broader and really look into some of the other techniques which have some interesting applications. So, for example, VLBI, SLR, satellite laser ranging, borehole strain meters, leveling, tilt measurements, electronic distance measurements, photogrammetry, triangulation, paleo deformation, seafloor geodesy. So we'll look through these more or less sequentially. And we start with the GNSS system. So many of you may know the GPS positioning. We have it in our phones, and it helps us to navigate and find our way around. But this technique can also be used for high precision geodetic measurements. So nowadays we talk about GNSS measurements, stands for Global Navigation Satellite Systems, and that is because there are a few of them. There's the GPS system, that's the United States system. We have the GLONASS from Russia, Galileo is the European, Beidou from China, and then NAVIC and the QZSS from India and Japan, respectively. So these systems all have in common that there are satellites that are orbiting Earth at a relatively high altitude, so about 20,000 kilometers from the surface of Earth, and they're broadcasting some electromagnetic waves, so in particular some pseudo-random code that's modulated on carrier waves. That's sort of key here. So this pseudo-random code shown here on this image is basically a row of ones and zeros, and each satellite is broadcasting these codes, and the receiver on Earth also generates the same code, and using cross-correlation we can find quite accurately the time difference between when the signal is broadcast from the satellite and when it is received at any given place on Earth. So this time difference is then used to calculate the distance to the satellite, and if we know the distance to one satellite, we're located somewhere on a sphere around it, and then if we know the distance to 2 and 3 satellites, we can narrow down the position quite well. We need a fourth satellite to correct for receiver clock error, because the GNSS satellites have atomic clocks on board, but our phones do not have atomic clocks. So in practice, one just observes signals from as many satellites as possible. And in general, the position is affected by some signal delays. It's a timing system, and the ionosphere and troposphere affect this. There are also some signal reflections or multipath that needs to be taken into consideration. And then we can have clock errors, orbit errors, antenna, maybe not errors, but some different characteristics of the antennas. And then it's also important that wherever we set up our DNSS antennas, that we have good stability of the monuments. So dealing with the atmosphere, so there are two parts of the atmosphere that come into play when we're working with DNSS data, and that is the ionosphere, which is relatively high in the atmosphere, so the signal gets delayed by going through there. And it also gets delayed in the troposphere, the lower part of the atmosphere. So the ionosphere is what we call a dispersive medium, so radio waves with different frequencies move at different speeds through it. And so fortunately the GPS and GNSS systems, they broadcast in at least two frequencies called L1 and L2, and we can use them to reduce these delays or atmospheric errors. In the atmosphere or troposphere, we have these sort of mesoscale variations in water vapor. Water vapor has quite an effect on the propagation time of electromagnetic waves, and there are some special means that need to be used to reduce those effects. But in general, these tropospheric and ionospheric errors are some of the largest error sources in high precision GPS applications. So if we want to achieve millimeter accuracy, measuring plate motion and volcanic deformation very accurately, then we need to use the so-called signal carrier wave. So we talked about this pseudo-random code that's embedded on a carrier wave, which has a much higher frequency. And if we can really track that frequency really well, we can simply get more accurate positioning. So the effective wavelength of the code is something like 300 meters, whereas for the carrier wave it's like 20 centimeters, 25 centimeters. So that is really key to getting this precision positioning that we really want. So in the end, we get some sort of time series. To get accurate time series or accurate positioning, we need to collect data over a day or so, 24 hours at least. And then we form this time series of change in position as a function of time. If we take the slope of these time series, we get the movement velocity. But we may also be interested in offsets, earthquakes, or eruptions, or just some other time variable changes. So here's just an example of how these can be used. These are DPS-derived velocities in southwest Iceland, which are plotted here relative to the stable North American plate. So all the sides that are moving to the east and sort of southeast, they are on the Eurasian plate. So these are just direct measurements, and they're really showing where the plate boundary lies in southwest Iceland. Okay, to summarize, so there are geodetic quality measurements that we get from GNSS. This is sort of an all-weather, all-season application. We can run this instrument continuously or semi-continuously, or we can just go and visit benchmarks every 1 or 5 or 10 years, whatever. We can also run these with high sampling rates, so we can look at seismic waves with this kind of data. And if the benchmark is well located, there's good long-term stability. But a problem maybe with this technique is that these are always point measurements, so one needs to go to the particular location. So let's look at a different technique. So INSAR, interferometric synthetic aperture radar, and principle here is that two data acquisitions at different times are taken from similar or as similar as possible locations of the satellite. And the primary observable here is the radar signal phase. So many think about the radar as maybe being amplitude, but we're really looking at the wave form that is reflected. And it's an interferometric technique, and it enables detection of surface deformation with sub-centimeter level accuracy. And really each point on the ground can become a measurement point with anyone needing to go there. We just use the reflected signal. So this allows us to get very good spatial coverage, but there can be all sorts of problems with vegetation or snow cover issue, or the reflective points are maybe not in stable slopes, etc. So here's an example interferogram from an intrusion north of Vatnajökull in Iceland. We look at some more interferograms like this. So the principal sort of geometry is that these satellites are flying at maybe 400 kilometers height. They are on so-called polar orbit, so they orbit the poles of the Earth. And they broadcast the radar signal usually looking to the right as they're flying along their path. So they broadcast the radar signal and receive it under some particular look angle. And that means that it measures a combination of deformation in the vertical and horizontal directions, and this is called the line of sight deformation. It measures this deformation in the line of sight. So the radar signal illuminates some part of the ground, and this footprint, if you want, is different between the different types of INSAR satellites. Sometimes it's large, sometimes it's rather small. So it's an interferometric technique. If people remember what is the Michelson interferometer, it's a sort of common physics experiments that is sometimes done. So seen here on the right, so look at a test surface, how if that is moved by tiny amounts, then there is a fringe pattern formed by the constructive and destructive interference of light. Addition of waves, basically. So the same principle applies when using INSAR data. We really are looking at differences in small displacement and how the phase or wave parts of the signal, how they are slightly offset as the data are collected at different times. And it gives us this sort of characteristic pattern from this technique. And the INSAR also deals with similar error contributions as the GNSS systems. We need to think about the troposphere and ionosphere and orbital errors, and we can also have some errors just from incoherence. So if the reflective properties change, we might not get the same same reflections back at different times. So here's an example of some fringes, or that's what we call these changes in color scale. So one complete change in color scale here corresponds to a few centimeters of deformation. This is from a dike that formed in 2014 at Bárðarbunga, Iceland, a 45-kilometer long dike. And we see that in the main figure as the distance between each fringe is getting smaller and smaller, means that the deformation is getting larger and larger. So sometimes people talk about unwrapping these data, and that basically means the process of going from these kind of fringes and towards total displacements in the line of sight seen here on the right. So there are some different radar satellite systems that exist, and they all have some limited lifetime. And that means there are sort of patchy observations that we have for total deformation of different volcanoes, for example. So there can be the ERS satellites, Envisat, ALOS, TerraSAR-X, Cosmos SkyMed, RadarSat, Sentinel series, ICEYE, etc. And it's quite different how easy it is to access this data. Sometimes it's freely available, sometimes not. And these satellite radars also operate at different frequencies, called the L, C, and X bands. And that affects the resolution and sort of the reflective characteristics that each system gives. And to process this data, first step is to find out what data exists and establish access to that data. And then there are different processing softwares to choose from. Many use the ICE software, but there are many other options. And there are also many options of how the data can be processed. We can do one-to-one interferograms, just differentiating 2 points in time. We can do time series analysis or stack the data, use so-called persistent scatterers. We're really focusing on the best scatterers in the images. And we can also do what's called pixel tracking of the radar images, which we'll come to later. We have... because of the motion of the satellite, how they go around Earth in these polar orbits, we have what we call ascending and descending image pairs for the INSAR data. And that basically gives us at each region 2 different look angles, which we can use to separate these line of sight motion into near vertical and near east motion. And then finally, ground-based INSAR can also be used. So we can have INSAR systems just sitting on the ground if we want to monitor some flank very well. So now we move to some different techniques. So very long baseline interferometry is also an interferometric technique. It uses electromagnetic waves or radio waves from quasars, so distant stellar objects that are kind of fluctuating in their light output. And this light is correlated, and it allows the distance between 2 radio telescopes to be calculated quite accurately. And on the lower left here, there's a time series spanning about 25 years, showing the change in distance between a radio telescope in the United States and in Germany. So these are, of course, not practical if you're monitoring a volcano, but because these are huge radio telescopes, but they are used and are very important for some reference frame definitions, because how do we know where the GPS satellites and GNSS satellites are? Well, we use GNSS stations on the ground to track them, and we need some external reference like these very long baseline systems to be able to have a more stable reference frame. So laser interferometry can also be used in different modes. Here's an example just from detection of gravitational waves from 2015. Very accurate measurements or precise measurements with tiny amounts of strain, so spanning very short time. So this is basically deformation observations of gravitational waves, first to be made. Another technique is called satellite laser ranging. That's also not very practical for deformation measurements because there are telescopes that are shooting lasers to special corner reflector satellites and just measuring the time of travel in between. This is included mostly for reference frame definitions. And the final sort of space geodetic technique that I was going to talk about is called DORIS. It's sort of the inverse of the GNSS systems in the manner that the transponders that broadcast the waves are on the ground and the receivers are in the satellites. So there is, for example, a DORIS station in Iceland and some other places around the world. This is not frequently used for crustal deformation, but important for verification of GNSS and definition of reference frames. So these were sort of the space geodetic systems, and here are some exercises that you can do to expand your knowledge and to work on in your own time. So thank you.